Alrighty, so in this video we will kind of go over a very general overview of the standard model of particle physics. Basically, physicists generally, they want to try to condense down all the laws of physics to their most fundamental forms. We want to know why things work the way they work, what's the most fundamental nature of the universe, and then understanding that, does that give us better insights to the more macroscopic things we see? So, for instance, is it possible to understand how the galaxies form, why the universe is the way it is, how even chemical reactions occur, if we understand how particles interact in their most basic fundamental nature? What are all the particles in the universe? All the different forms of matter we can have? What are the forces that mediate the different interactions? All these types of things. If we can understand nature at its most fundamental, then perhaps we gain better insight, better conceptualization of more complicated parts of the universe. And that's kind of the point. We want to know what are things made of and how do they interact. So that's what the standard model is all about. Everything we see in the universe can be boiled down to a very small set of things, which is surprising. In fact, even in the field of particle physics, it started fairly simple, but then particle physicists, experimentalists would find more and more particles that exist, and we were getting hundreds, if not thousands, of different particles, and that's a very complicated situation. Fundamentally, we don't just have things like protons and neutrons and electrons, but maybe there's these things called kaons and pions and all these sorts of things. However, thankfully, as these particles were studied, their interactions and all sorts of things, physicists started to realize that actually, no, all these particles can be made of even more fundamental pieces. And so the race was on to find out what are the most fundamental things. Just like we have, molecules. Molecules are made of different elements, different atoms. Atoms have nuclei and they have electrons orbiting them. Well, is there something inside of the nucleus? Yes, we found out there's protons and neutrons inside. Are protons and neutrons fundamental like the electron? Well, eventually we found out no, protons and neutrons are made of things. Quarks, of course. Well, are quarks made of things? Well, as far as we're aware, in the standard model, that is, the things we can prove for sure, it turns out nothing makes up a quark. A quark is its own fundamental particle. However, this may be true, this may not be true. It's just that to the level of experimentation and theory that we've gone, we do not see that quarks are made of even more fundamental particles. Is it possible that one day we will discover this isn't true? That's starting to get philosophical, as we will see as the class goes on. Because how do you detect if something is composed of particles? Well, usually, say you have an atom, has a nucleus and electrons orbiting around, let's say. How do we find out if a nucleus is composed of things? Well, we hit it with particles. We hit it with, let's say, a neutron, not a neutron, let's say another atom with electrons floating around and whatever. We throw this atom at the other atom, and what do we find? We find that pieces come off. Right? Little pieces of this nucleus, when it eventually hits the nucleus, which is a rare event. It's rare because the vast majority of an atom is space, empty space, and the nucleus takes up a very, very, very tiny, minuscule volume of that atom, so it's hard to hit it, but once you do hit it, you get pieces flying out. And so we say, okay, well that means this nucleus was composed of these other pieces. Eventually we named them protons and neutrons. And again, we then look into the nucleus and we say, okay, if there's a proton, so here's a proton, we want to know, is it made of stuff? So again, we throw something at it, some particle, maybe another proton, maybe it's a neutron, maybe it's an electron, whatever it is, and it hits the proton, and we see, does stuff come out? And this is kind of more complicated, but yes, eventually we find out particles come out of this, and these particles we call quarks. Now, I'm super simplifying because there are rules about how the quarks come out, and we will go through as we study the Standard Model. So the question is, well, quarks, if it's possible to hit a quark with something, would something come out? It turns out yes, but that doesn't necessarily mean that thing was inside the quark. Because, as we will see, we have things like E equals mc squared that kind of relate energy and matter together. And as you start to throw things at these quarks, the quarks are so tiny that in order for something to hit it, that's something, let's say we hit it with light. This is an easy explanation. Of course, it's more complicated when we get into hitting it with other matter. But if we want to throw light and see the quark, that light's wavelength has to be small enough to be able to detect the quark. That is to say, if the wavelength of light is bigger than the quark, it doesn't interact. It just goes right through. You don't see it. It doesn't reflect off. So you need wavelengths smaller than the size of the quark. Well, the smaller the wavelength, the more energy the photon has. And the more energy, if you put too much energy in one spot, then you wind up creating more particles. So if we have a quark, let's say, and we throw, here's a photon, we throw a photon at the quark, and that photon is super, super high energy, and we see particles coming out. The question is, were these particles part of the quark itself, like in these past experiments where we hit a nucleus and protons come out, or neutrons come out? Or is it that the energy of the light was so high that when it contacted the quark, and basically all that light was in a single spot, it created an electron-positron pair? And so this light, which is pure energy, creates matter whose energy is the same as the energy of the light itself, and thus you get these particles created, not because they were inside the quark, but rather because they were created by the energy of the light itself. So again, this is kind of philosophical. Was this quark composed of these particles, or was it just a side effect of the amount of energy necessary to look at this quark that you get these particles being created by the light itself? These are questions that need to be answered, of course, and more experimentation gives rise to more and more answers for us. Anyway, all this is to say, the point of particle physics, the most fundamental version of physics we can get, is to try to describe the universe as a whole, every single aspect of it, in its most fundamental way. So the first thing we want to do is talk about, well, what are the parts of the Standard Model? And for that, we basically have two big categories. And now, when we talk about particle physics, it's in the name, everything is a particle. Now, truly speaking, it's kind of odd or ironic, but particle physics, which in the name, like I said, is all about particles. Forces have particles, particles are created of particles, everything's particles. Actually, particle physics is a field theory. Field theory. That is to say, we've all heard of the electromagnetic field, or the electric field, the magnetic field, gravitational field. There's things like the wind velocity field, the temperature field. Fields just mean that in space, there exists at every point some amount, some magnitude, if we're talking about scalar fields, or magnitude with direction, if we're talking about vector fields, whatever it is, there's some value of this field everywhere in space. So if it's the electric field, it basically, let's say we have an electric field that looks like this. That is, if this is space, here's X and Y, then if I were to put a particle here that's positively charged, the electric field tells me what kind of force would this charged particle feel. It would feel a force directed in the direction of the electric field line, and the magnitude of that force is proportional to the length of the electric field vector, or the magnitude of the electric field at that point. Okay? Same with temperature. At every point in your room right now, you have a temperature. Now, closer to the window, it might be warmer. Closer to the AC vent, it might be colder. But at every point in space in your room, there's a value, and that value is the temperature at that point. So there's a field describing the temperature. Okay? So fields everywhere. Fields are very, very important to physics. There's classical field theory, quantum field theory, all sorts of stuff. It turns out particle physics is truly, at its heart, a field theory. Everything is a field. There's a field for everything. And in space, let's say in your room, right next to your face, there is a value which tells you something about the electric field. There's another value that tells you about the magnetic field there, a gravitational field, but there's also values like the quark field, or the Higgs field, or all sorts of different values, each one associated with its own little particle. And if you excite this field, then you get a particle associated with that field. So a photon, a particle of light, stems from the electromagnetic field, and it's an excitation of this electromagnetic field. That is to say, you put enough energy, you excite the electromagnetic field, and what we see as this excitement of the electromagnetic field, this value in the field, is a particle of light. That's how we see it. We view it as a particle. But it's just like an amplitude in the field, a wave moving through the field. That wave, that amplitude of the wave, is the particle that we see as the excitation of the field in that location. Okay? But that's the truth. However, for our purposes, we're just going to be discussing, for the most part, particles. But again, remember, deep down, kind of behind the scenes, everything's truly a field, and particles are just a representation of that field. Okay? So, as I was saying before that little aside, we have two major categories in particle physics, in the Standard Model. The first are the fermions, and the other is the bosons. So everything we're aware of, everything we have experimental evidence of and theoretical, everything is either a fermion or a boson. The names come from fermions obey what's called Fermi-Dirac statistics. Okay, whereas bosons obey Bose-Einstein statistics. Now, what that means, they obey this type of statistics. What it means when I say that is there are certain rules that must be followed, and the rules for fermions, Fermi-Dirac statistics, have slightly different rules to that of the Bose-Einstein statistic particles. For instance, fermions one of the results of the fact that they obey Fermi-Dirac statistics is they follow the Pauli exclusion principle. Now, of course, if you're a chemist, then you know for sure what the heck the Pauli exclusion principle is. It's a very important part of how electrons behave. Pauli exclusion principle basically says no two particles can be in the same quantum state at the same time in the same location. Okay? So you can have, let's say, in an atom, electrons are orbiting the nucleus, and they have different energy levels, different orbitals. The rule says, of course, electrons want to be in the lowest energy state possible, the ground state. However, Pauli exclusion principle disallows every single electron from being in the lowest energy state, because if they're all in the lowest energy state, then they all have the same quantum numbers. They all have the same quantum state. So what has to happen is one electron comes into the ground state, the next electron that comes in has to have a different quantum state. It can still go into the ground state because it turns out that the ground state has two energy levels, or not two energy levels, but two states, two spin states. But then once you get the third electron, there are no more states available, and it can't have the same state as one of the other two, so it must go into the next orbital, the next energy level. And that's why you have different orbitals for the electrons. Because for whatever reason, the universe dictates that if you have whatever characteristic we're about to find out, which creates fermions, then that particle cannot have the same quantum state as other particles. Okay? Bosons, that's the exact opposite. Bosons can have as many particles in the same quantum state, can have the same quantum state. Okay? And you have very special forms of matter called Bose-Einstein condensates and all sorts of things. This is why we get things like superfluids and superconductivity and all sorts of fancy things. So that's the big difference. Fermions, Fermi-Dirac statistics, bosons, Bose-Einstein statistics, and that would, if you follow the rules, if you follow the mathematics behind those two mathematical systems, then you will follow the rules of how these types of particles will interact with each other. What is the major thing which decides whether something's a fermion versus a boson? It's its spin. Fermions all have half-integer spins. So spin 1/2, 3/2, 5/2, -1/2, things like that. If a particle has a spin 1/2 or any integer multiple of the half integer, so spin 1 is a multiple of a half integer, but it's an even integer. You want odd integers. So if you have odd multiple half integer particles, then those are all fermions. Bosons, on the other hand, are integer spins. So spin 0, spin 1, spin 2, things like that. Okay? That's what dictates which form of the statistics, which form of interaction the particles will follow. If it's a spin 1/2 particle, it's a fermion, and it responds to the Pauli exclusion principle. If it's a boson, it's an integer multiple, so it's a whole number, and it does not follow the Pauli exclusion principle. Okay, that's the two big things. So first, we will go through the fermions. Now with fermions, there's two major branches. Okay, there's the quarks, and then there's the leptons. All right, so fermions, there's two types. There are quarks and there are leptons. What do we know? Well, leptons, those are easy. Those are the things that are like electrons. Okay, so electrons are an example of a lepton. Okay. Quarks, there's various types, but these are the things that make up protons and neutrons and other things like this. Okay? Now, what is the big difference between the two? I mean, if they're both fermions, what separates quarks from leptons? Well, quarks obey or interact via the strong force. And we'll get to what this force is later. Whereas the leptons do not. Leptons do not feel the strong force. Quarks do feel the strong force. Other than that, they both feel the other forces, the weak force, the gravitational force, the electromagnetic force. They all feel it, but only the quarks feel the strong force. So that's kind of the big thing between the two. What else do we know? Well, under this branch, the fermion branch, you have the quarks and the leptons. The quarks give rise to its own little branch, and that's called the hadrons. Hadrons are those particles, those, not elements, not molecules, yeah, let's say particles. Those particles which are created from quarks, okay? So a proton is made up of quarks. It's a hadron. Okay? A meson, another particle we'll talk about, is created from quarks. It's also a hadron. They're different, and we'll see how they're different, but hadrons are the set of particles made up of quarks. Okay. Now, under this branch, and this, of course, this is all names. This is starting to get like biology, where we have kingdom, phylum, class, order, family, genus, species, all those things, categories. This is all just to kind of organize things. So, yes, you should know these names. You should know what they mean. That way, if you discuss particle physics with someone who knows particle physics, then you're talking the same language. The names themselves are not very meaningful, especially as we get to the names of quarks and things like that. They're completely ridiculous. They don't necessarily mean anything by the name. However, we have to categorize things, so we have names for them. So, fermions, there are the quarks and the leptons. Those things created out of quarks are called hadrons. Now, under hadrons, there's two major types of particles created from quarks. They're all hadrons, but we have baryons and we have mesons. Okay. Both of them are created out of quarks, so they're both hadrons, but a specific type of hadron is a baryon. What is a baryon? It is any particle created from odd number of quarks. Usually 3, but of course it could be 5, it could be 7 as well. For reasons we will discuss, there's no such thing as a single quark. You can't have a baryon made of one quark. That's an odd number, but it's too few. We've never, ever seen in any experiment at any energy level a single quark by itself. They always come in sets. If it's a set of 3 or 5, almost all of them are 3s, then we call them baryons. Okay? Protons are baryons. Neutrons are baryons. Okay. The other type, the meson, is created, obviously, from even number. And the most likely to be seen is 2. 2 quarks making up a meson. Now, technically, it's a quark and an anti-quark. This is the symbol for anti. You put a little bar on the top. So something like a pion is created from, let's say, an up and an anti-up, if we want to call it that. That would be, that would be a meson. Two quarks, and for reasons we will see, it has to be a quark and an anti-quark. But two quarks make up mesons, three quarks make up baryons. The normal particles in our universe, all the atoms, every piece of matter you can find, is created out of protons and neutrons, so they're all baryons. We have seen mesons, and mesons play a very important role, but they are kind of short-lived, and so under normal circumstances, you've never seen a meson. There's nothing, there's no part of your computer, there's no part of your bread that's created out of mesons. It's just baryons. However, mesons do exist, and they exist in reactions, interactions between things. All right, so those are the quarks. Quarks make up hadrons. So the quarks are the fundamental bit. Hadrons, there's two types. You've got baryons, which are the three quark guys, and you got mesons, which are the two quark guys. And then you have the leptons, and those are the electrons. And so every atom, which is a nucleus with electrons orbiting around it, is a fermion, or depending on how you do things, they're like fermions. They're quarks and leptons put together, baryons with leptons, and so forth. All right, now the bosons, on the other hand, these are interesting. These are kind of weird. These are the things that you're not really used to thinking about as particles. Okay? Fermions, almost no one has trouble thinking about these as particles. They're protons and neutrons. They're quarks. They're electrons. Obviously, we think of them as particles. Bosons, on the other hand, are not your standard particles. Bosons are what we call the force particles. Or the mediators, or the interaction particles. These are the particles that allow fermions to interact with each other. Of course, you could also have bosons interact with bosons too, but usually what we think of is something like you have an electron, or you have two electrons interact with each other. They, by the Coulomb force, they repel each other. The reason they know the other electron is there, the reason they have this interaction, is because some boson, some force particle, the photon, between the two, mediated this force interaction. So you can think of it as, if you are on an ice skating rink, so here's you, and you're holding a ball, and here's someone else. You throw the ball to this person. Well, we know, and this is an ice rink, so there's no friction here. We know that by Newton's third law, when you throw the ball forward, the ball pushes back on you, and so you move backwards. And then the person you threw the ball to, when they catch the ball, by conservation of momentum, they have to move backwards as well. And so you could think of this ball that you threw to the other person as the boson. That is the force particle, the mediator, which causes you two to repel. Okay? So if instead of you and some other person throwing a ball, it's an electron and another electron, and a photon was passed between them, that's kind of the picture you can have in your mind as to why two electrons repel each other. Now, obviously, it's way more complicated than that, and that's just a simplified model, because then how do you explain a proton and an electron? They should attract each other. How can you attract if you're throwing a ball between each other? You necessarily have to move away. So there's ways of kind of explaining it, but for the most part, this is a nice simplified image of what it means to be a boson. This guy, the ball, is the boson. And the two people throwing the ball back and forth, those are the fermions interacting by this boson. All right, so those are your two major states. The matter stuff, which are the fermions, and the force stuff, which are the bosons. Now, let us create the chart. This is the famous chart, the standard model of particle physics. It, as far as we're aware to this point, contains every fundamental particle we're aware of. Okay? Everything else is made of these. And so usually what we'll have are the fermions over here. So we'll have the fermions on the left, and we'll have the bosons on the right. We have the quarks and the leptons. Okay? And so it looks something like this. In fact, we don't even need this here. So for the quarks, what do we have? It turns out that the vast majority of all quarks, of all matter in this universe, is created of just two quarks. There's the up and the down. Again, here's the naming convention thing. Stupid names, it's just to label them. There's nothing about upness or downness, directionality. It's just two names. We could call it cookie and cheese, and it's the same exact thing. It doesn't matter. So these two quarks, up and down, comprise all the matter we know about, pretty much, that we see in our everyday lives. Some information about the up and the down. First of all, they both have charge. The charge of the up quark is plus 2/3 times the fundamental charge, which is the charge of an electron or the charge of a proton. All right? Electrons and protons have a certain charge, and everything we know about, before we get into particle physics, is some integer multiple of that charge. Well, it turns out that quarks don't obey that rule. They don't have an integer multiple. They actually have a fractional charge. But it turns out that because of how quarks always group together, no baryon and no hadron created from the quarks will ever have a fractional charge. They will always have an integer multiple of the fundamental charge. But one single up quark by itself is 2/3, and a down is minus 1/3. Okay? That's the charge. And again, because they're fermions, we know these are spin 1/2. So the up quark has a spin of 1/2, the down quark has a spin of 1/2. Leptons, what do we know about them? Well, the big one, the first fundamental one, is the electron. He's the big guy. And with these three particles, we now have the 99.9999%, well, that's not really true. A vast majority of all the matter in the universe is made up of ups, downs, and electrons. Okay? Again, the electron, he's got a spin minus 1 times the fundamental charge. He's got the charge of an electron. Of course, he's the fundamental charge. And again, he's got spin 1/2. It turns out there's another lepton associated with the electron, which is a little weird, and this is called the electron. That's the symbol for the electron, E with a little negative superscript, neutrino. Now, the neutrino is a very, very weird particle. We know it exists. The problem with it is it does not interact in any way with any other particle except by one mechanism, and that mechanism is the rarest of all the forces. It's called the weak force, and we'll get to it. But because it's so rare for this interaction to occur, we almost never, ever detect neutrinos. We do detect them, but it's rare, it's hard to detect, it's very difficult to see these in experiments. theoretically, from the analysis, from the mathematics of particle interactions, we know they have to exist, and we know some stuff about it. First of all, it used to be thought, in fact, I think it's within my lifetime that they found out it's not true, but they used to think neutrinos had no mass because they move so fast, so close to the speed of light, people thought it was the speed of light. But no, it turns out they move slightly slower than that because they're so light. We now know they do have a mass, but that mass is extremely tiny. So they do have a mass, but they have no charge, zero charge. They're neutral, thus the neutrino part. And ino just means it's a very tiny particle. So it's a little bitty neutral particle. Okay? So that is what we call the first generation of fermions, or the first family. It turns out there's 3 generations. Interestingly, the next generation is almost identical to the first. We have 2 quarks. The first one we call the charm. Sometimes charm, sometimes charmed. Again, very weird name. But it is what it is. It's called the charmed quark. It is very similar to the up quark because, again, it has spin 1/2. Again, it has a charge of plus 2/3. The difference between the up and the charm is that the charm is much heavier. And what we're going to find is that what usually happens in the universe is that particles always decay, or try to decay, to their lowest energy state or their lowest mass state. So just like electrons orbiting atoms, or orbiting a nucleus, those electrons always want to get down to their lowest energy level. Well, the same is true for quarks generally. If you have a really heavy version of a quark, well, it wants to kind of shed all that extra energy, get rid of it, and become the lightest version of itself. So the charm, being very heavy relative to the up, eventually will decay into other stuff and become an up quark. The version of down is what we call the strange quark. And again, just like the down, he's got minus 1/3 charge. Okay, so that's the second generation of the quarks. Almost a mirror image of the up and the down, except instead of up and down, we've got charm and strange that are heavier than the up and the down. So they will almost immediately decay down into a bunch of particles, plus creating up and downs. And just like protons and neutrons are created out of ups and downs, some combination, we can have particles created out of charmed and strange, or charmed and down, or up and strange, or all sorts of different combinations. It's just that in your everyday life, you never see a particle that has a charmed quark or a strange quark, because they've decayed already. The second generation of the leptons, we have the electron and the electron neutrino. The next one is the muon. So the muon is just like the electron. Again, charge -1, spin 1/2. It's a lepton, except it's a heavier version of the electron. Okay? And the neutrino, there's the muon neutrino. Charge 0, spin 1/2, and it acts just like the electron neutrino. Okay? But it's associated with the muon version of the electron. All right, and then the final generation, the third family, we had up, down, we have charm, strange. The last 2 are top and bottom. Originally, or when they were first being named, they kind of, physicists, weirdos, wanted to continue the whole weird name thing with charmed and strange, and so they tried to call it truth and beauty, but thankfully that was overruled, and so they went down to the up and down type convention and call it top and bottom. So top is like the up quark, plus 2/3 charge, spin 1/2. Bottom is like the down, minus 1/3, spin 1/2. But they're the heaviest of the quarks. Okay, so it was only fairly recently, I think 60s or 70s, that they were even detected in the lab. Of course, they were theorized before then, but because they were so heavy, it was very difficult to find them. You had to have enough energy to create a particle of its size. And of course, even if you do, that particle decays so fast that you have to detect it quickly. All right, the final lepton is called the tau. And of course, there's the tau neutrino. Zero charge for the neutrino, minus 1 for the tau. And again, it's just like the electron, but heavier. Okay, so there's your three families. You've got the up, the down, and the electron stuff. Charm, strange, and muon stuff. And then top, bottom, and tau stuff. All right, so those are the fermions. Everything else, all the other matter in the universe, is some combination of these things. So there are things in the universe called pions, different versions of pions. Some are positive, some are negative, some are neutral. How do you get a pion? Well, a pion is a meson, and I know from the definition of a meson, it's a quark and an anti-quark put together. And so if you have an up and an anti-up, that would create a pion. A proton, well, what do we want? How do I figure out what a proton is made of? Well, I know a proton is a positively charged baryon, so I have to get 3 quarks. And protons are stable, so they can't be the heavy guys. They have to be the fundamental ones. So I need 3 quarks. When added together, give me a charge of +1. So I would look at this chart. I'd say, okay, well, I'm not going to look at the leptons because it's made of quarks. How do I get a charge of +1? By adding 3 of these ups and downs together. Well, if I add 2 ups, so 2/3 plus 2/3, and then I subtract off 1/3, well, that's 4 minus 1 is 3/3, which is a charge of +1. So a proton is nothing more than an up, and a down quark. Okay? And then likewise, you can have an up, and a strange, which is something that's very similar to a proton. It's got the same charge, but it's more massive, and it's unstable, and there are other little conservation laws we got to worry about later on. But for now, this is kind of the picture you should have in your mind. If I'm going to create a piece of matter, some particle, it's going to be made up of quarks and leptons in some way. If it's a baryon, we've got the 3 quarks. If it's a meson, it's 2 quarks. If it's an atom, it's got leptons in it. All sorts of different things. Bosons, spin 1. Well, in fact, let me not even write that yet, because we'll see why. The bosons being the force-carrying particles, it turns out that there are 5 bosons we know about. That's not true. I should say there are 4 forces, and there's a boson for each of the forces, plus a few extra that we'll see. So the first one we want to know about, the important one, is, let's say, the strong force. I'm not going to go into too much about what the strong force is yet, but the strong force is basically that force which holds the quarks together. It's the reason why we can create protons and neutrons, and why the nucleus holds together in an atom, even though everything inside the nucleus is positively charged or neutral. You would think it would explode from the Coulomb force, but no, they hold together. And they hold together because there's a strong force. The particle that's associated with the strong force is what's called the gluon. Gluon. Okay, so sometimes you'll see it as G. The gluon, it is a boson, so it's got to spin 1. And it turns out, no charge, charge 0, and mass is 0 as well. I'm not writing the masses of the quarks and the leptons because who cares? If we were doing true experimentation, then of course these numbers are important because the energy of your experiment has to be associated with the particles you're trying to create. But it is interesting to note that the gluon has no mass as far as we're aware. Okay. So that's the particle for the strong force. The next one, electromagnetic force. So of course this is the guy associated with the Coulomb force. It's light. It is our ability to see things. It is any kind of interaction that has to do with charges. This is the force associated with it. In fact, it's almost every force you could think of. You sitting on a chair and not falling through is kind of guided by this electromagnetic force. Okay. The particle, the kind of symbol for it is the photon, gamma. The photon. Of course, its spin is 1. It's a boson. Charge is 0. And mass is also 0. It better be 0 because it goes at the speed of light. It is light, and so its mass better be 0. So that's the electromagnetic force. The next force is the weak nuclear force. This one is a little bit more complicated because there's various particles associated with it, but there's basically 2 types. There's the Z and there's the W. Okay? These are called gauge bosons, but these 2 are a little bit weird compared to the other ones because they do, in fact, have mass. They have a mass. Some have charge. Okay, the spin is still 1, so that's nice because they are bosons. But these guys are the reason why we have things like nuclear decay. Maybe a neutron decays into a proton plus positron, or plus an electron plus an electron antineutrino. The reason this nuclear decay happens is due to the weak nuclear force. And unlike the other forces, this force has different particles which mediate the force. So every single interaction that's electromagnetic is always associated with a photon. The photon is the only guy who does it. Gluons, if I have 3 quarks, they're being held together in the nuclei, or in a proton to create the proton. The only particle that's sitting there doing this is the gluon. Now there are different versions of gluons, as we'll see when we get to quantum chromodynamics, but they're all gluons. The weak force is unique in that there are 2 different types. In fact, there's actually, I think, 4 different types, or 3 different types. There's a positive W, a negative W, and then the neutral Z. So 3 different particles. All 3 of them can cause the weak force. It's just that which one of them is mediating this particular interaction depends on the charges at play. So for the neutron going to a proton plus an electron antineutrino, well, if you had the neutron and it goes to a proton, notice you're going from 0 to positive. Well, that causes you to need a negative mediator. So you would get a negative W come out, in that negative W decays into the electron and the antineutrino. Okay? Whereas if you had the proton going to a neutron and giving rise to a positron and an electron neutrino, you're going from a positive charge to a neutral, so the mediator has to be a positive W. And a positive W is the one that goes and decays into the positron. We'll see this more when we do things like Feynman diagrams. But for now, just know, unlike the other bosons, there's 3 different ones for the weak, 2 different W's and a Z, and it all depends on the charges of these interactions. But all of them have a mass, and all of them are the reasons for these nuclear decays. The final force, of course, is gravity. This guy, I'll call it capital G because we don't have a really good name. And this one also, sometimes you see it on the standard model, sometimes you don't, because technically we haven't really discovered in an experiment the graviton. That's what it's called, graviton. But we're assuming by theory it exists, since all the other forces it exists. Particle versions of them exist. Gravity is a field, and thus an excitation of the field should give rise to a particle. We're just calling it the graviton, and we're just waiting until we have an experiment that we can create one. So all 4 forces, there they are: gravity, weak, electromagnetic, and strong. Each one has some particle associated with it that mediates the force, mediates the interaction. There's one more boson, and that's the Higgs. This one's slightly different because we don't really associate it with a force. It's not like an electron and a positron interact with each other using the Higgs field, but rather every particle that has mass interacts with the Higgs field just naturally, and the effect of this interaction is that we see the particles having a mass. So the way to think about it is this: things that are heavy move slow, things that are light move fast. In fact, if you have no mass whatsoever, you move at the speed of light. So the question is, why doesn't everything move at the speed of light? What is this mass? Why does an up quark have a particular mass and a top quark has a different mass? An electron has a different mass. Where does this stuff come from? Whereas a photon does not have a mass. Well, it turns out the way to think about it is, let's say you could run on a track, and you could run at however fast you could run, but then you get into a swimming pool, and you try to run in a swimming pool, or you try to move, and you move slower, because there's a bunch of resistance against you. As you try to move through air, you can move a lot faster than if you try to move through water. So you feel as if you couldn't actually feel the wetness of the water and things like that, if all you did was look at how you move, how much force is required for you to move your arm or your leg, and how quickly it moves and the acceleration, then it feels as if you have more mass while you're in the water than if you were in the air. Now, of course, I have to be careful in how I say it, because that doesn't mean that when you're in the water you feel heavier, because in fact you feel lighter, you have the buoyant force. But what I mean is, in order for you to move your arm in the air, then you basically just have to push or use a force equal to the weight of your arm, or more. Whereas if you're in the water, you have to move with the weight of your arm, plus going against the resistance due to the water. Or if you're on let's say you're riding a bike, as you ride a bike with the wind, it's really easy. But then you go against the wind, and now it's more difficult. Just like if you're pushing a really light object, it's easy. If you push a really heavy object, it's more difficult. So the Higgs field is kind of like that. When a particle interacts by the Higgs field, or interacts with the Higgs field, it moves more sluggishly. It slows down. It's harder to get, it has more inertia. And so it's harder to move it, or at least it's harder to change its motion. And the way we see that, the way we kind of interpret this, is as a mass. This particle interacts a lot more with the Higgs field, so it's as if it has a lot more mass, or at least that's how we interpret it. Okay, so the Higgs is another boson. That's capital H, Higgs boson. Slightly different. First of all, the Higgs boson is the first of our bosons that we've seen that has spin 0 instead of spin 1 or spin 2 or things like that. It's still an integer multiple, 0, so it's still a boson, but it's spin 0. So the Higgs boson is that excitation of the field being the thing which gives rise to this phenomenon we see as mass. Okay, that is the Standard Model. So if I write it a little bit more neatly, we have the up quark, the down quark, the charmed, the strange, the top, the bottom. We have the electron, the muon, the tau, the neutrino electron, the muon neutrino, and the tau neutrino. Okay, so those are my fermions. And then for my bosons, I've got the gluon, I've got the photon, I've got the W and Z, I've got the graviton, and then I've got the Higgs. Gluon, photon, W and Z bosons, graviton, and Higgs. Sometimes, like I said, these are a lot of time called gauge bosons. And that is everything we know of. There are theories to extend this, and in fact, like I said, graviton, should it technically be on the chart since we haven't actually in the lab discovered it? Probably not, but we're confident enough that it should exist that we just include it. But if you see tables online or whatever, in fact, I've got a t-shirt, and I think the t-shirt doesn't even have the graviton on it. If you see it doesn't have it on it, that's why. Because usually what they try to do is the Standard Model are those things that have been experimentally verified. In fact, before 2017 or whenever it was that the Higgs was seen in the lab, everybody knew the Higgs boson should be there, but it wasn't included on this chart because it hadn't been found yet. Of course, now it's been found, and so now they can include it. However, before then, even though we knew it existed, theoretically, and obviously my bias as a theoretical physicist is that's way more important than just experimentally verifying it. We knew it was there. But we did discover it, which is good. Now, as an aside, for me personally, I was hoping we wouldn't. I wasn't a part of it at all. I was hoping physicists at CERN would never find the Higgs boson, because that's interesting. Here's something that the theory said should exist, and we could do calculations and say, okay, it should have a mass of about this much. This is the spin it should have. This is the charge it should have. We knew everything it should be. Then we go into the lab and it's never found. Well, that means there's something in the physics we don't know yet. That's the exciting stuff. Of course, if you're an experimentalist, the more exciting thing is finding what you're supposed to find. That means your experiment worked. As a theoretical guy, I would have thought, or I would have been way more excited had they never found the Higgs, because now it's like, okay, well, what is it about our theory do we have to change? Do we have to discover to say why it doesn't exist? Anyway, that's just an aside. So this is the Standard Model of particle physics. Mass particles or matter particles on the left, force particles on the right. On the matter side, we've got the quarks and the leptons. The quarks are what makes up all the matter we see in the universe, things like protons and neutrons and atoms and all of that. This stuff on the right are those particles which are associated with every force interaction we can think of that we've ever seen. Okay? Now, other things, what will we see as we go forward? Well, I've talked about things like QED, which is funny because in math, QED means something completely different than in physics. In physics, is quantum electrodynamics, which is basically the field of particle physics, or the field of physics generally speaking, which deals with how photons interact with matter. Okay? So electron-electron repulsion, chemistry, all these types of things, anything that has to do with the electrons or anything that has to do with light interacting with stuff, that's quantum electrodynamics. This was made by my favorite physicist, Richard Feynman, which he got a Nobel Prize, of course. And it's a very, very nice theory. It is probably one of the most accurate theories in all of existence. And surprisingly, the super complicated math associated with it, for instance, if I want to ask if an electron interacts with another electron, what will happen? In order to figure that out, you have to find out what is every possible interaction that could ever occur, whether it's likely or unlikely, and add up the result of each one of those interactions, weighted by the probability of that thing happening, adding that infinite number of interactions together, and the result is what will be the interaction that actually occurs. Okay? And like I said, when we get to this stuff, you'll see it much more concretely. But this is a very difficult problem. How are we going to add up an infinite number of possibilities, each one with its own odds of happening, to get a final thing that's accurate to what really happens in real life? Well, Richard Feynman came up with a beautiful, simple way of visualizing it called Feynman diagrams. And if you've ever seen things that look like this, let's say you have an electron and an electron coming in. Let's make this a positron. So I'm going to change my example from two electrons to an electron and a positron. So that's a positron. So electron comes in, positron comes in, they annihilate each other, and you get a photon. That photon has so much energy that eventually it decays and creates an electron and a positron again. And this is one single example of an interaction that can occur between an electron and a positron. Okay? If I want to know what will actually happen if I get an electron and a positron, there's thousands, if not an infinite number. In fact, it is an infinite number of other ways this can happen. You can have light interact there. You can have light interact here. You can have this photon creates electron-positron pair here and then goes back into light again. Each one of these is a possibility to occur. So we have to add up all these infinite number of things to get the final answer. But what's nice and genius about the way these diagrams work is that you can look at the picture and from the picture write out this long, complicated integral. We'll call it d tau for now. And the answer to this integral is what you would expect to occur in this interaction. And all you have to do is look at the picture and say, okay, for each one of these kind of nodes where there are three things, electron coming in, a photon going in, and an electron going out, that's a node, that's an interaction point. Here's another one, here's another one, here's another one, here's another one. For each one of these, you have a specific term that you write down. For each one of these main lines, you have a term. For each one of these particles, these mediators, you have a term. And so you just look at the picture, You follow the rules. You say, okay, for every node, I write this thing. For every particle, I write this thing, blah, blah, blah. Plug it all into this integral, and then hopefully the integral is solvable, and we'll have our answer. That's going to be the main thing we discuss in particle physics, is how do we do Feynman diagrams, because they're very powerful. There's also something called QCD. Now, QCD, so quantum electrodynamics, is basically how do electrons interact. At their heart, of course, you could also have quarks interacting by the electromagnetic force and all sorts of stuff, but basically QED is all about electrons and how electrons and light interact with each other to create other particles or interactions or whatever. Quantum, or QCD, is quantum chromodynamics. And this is basically how quarks interact. Chromo, in the name, is telling you this has something to do with color. Now, I didn't mention this because it's just a complication, and we'll get to it when we get more detailed about each one of these particles. But it turns out that each quark, the up, the down, the charm, the strange, the top, the bottom, each one, there's 3 versions of. Or the way we think about it is there's 3 versions of. Each one is a color. So the up, there's a red, a blue, and a green. The down, there's a red version, a blue version, and a green, and so on. And now the reason, or a phenomenon that comes out of the fact that all baryons are 3 quarks and all mesons are 2 quarks, and you never get this single quark thing. One way that that is explained, I'm not going to say it's the reason, it's just a truism, is a particle, a baryon, or a particle can only be created if the total color of that particle is, let's say, white. Okay? So if you have a red, blue, and green version of these particles, when you combine them together, if I want to make a proton, I need 2 ups and a down. But it's not just any 2 ups and a down. You have to have a red, a blue, and a green thing. Now, does it matter if the red is the up or the down? No. You could have a red up, a blue up, and a green down. Or you could have a blue up, a green up, and a red down. Those 2 things are still protons, and they're completely the same as each other. There's no difference. But the mathematics behind how these interactions will occur are governed as if these colors exist, and these things can only interact with each other following the color rules. Okay, so quantum chromodynamics, more complicated than electrodynamics, but at its heart, it's basically like if you have a composite particle, that is to say a particle created out of fundamental things, so a baryon, a proton, you have a proton created out of quarks. That proton has to have a set of quarks that when you add up their colors together, you get white. Or if you have a meson, let's say you have a pion that's an up and an anti-up. Then the up, let's say, is red. The anti-up has to be anti-red. So technically there's 6 colors because there's the colors and then the anti-version of each color. So again, even for mesons that only have 2 particles, how do you get a white from only 2 of the 3 major colors? Well, you don't. What you do is you get the color and its anti-color. So you could call it black as if you're canceling the color out. Okay? But again, we'll get into this when we talk about the strong force and quantum chromodynamics and things like that. But those are 2 major fields. Quantum electrodynamics and quantum chromodynamics. Electrodynamics, that's basically how do electrons interact by the electromagnetic force. And the quantum chromodynamics is how do quarks and gluons interact with each other. That is the standard model. That's basically what I wanted to go over for now. This is the picture one should have in one's mind. Again, the most important things is this first generation, up, down, quarks, and then the electron and its neutrino. If you have that, and then the bosons, then you know pretty much everything you need to know for the normal state of the universe. All the other ones, the charm, the bottom, things like that, those are only relevant when you're getting into high energy stuff. So if you're in a particle accelerator, if you're in a nuclear interaction, things like this, or a nuclear reaction, things like that, that's where energies are high enough where you can get a particle whose mass is a lot higher than the normal ones, and thus can exist for some amount of time. So they're important. They do things, and there are phenomena that occur because of them. However, at the end of the day, almost everything is up, down, quarks, electrons, and their neutrinos. And then the forces. All right, so I hope that is useful. I hope it's understandable. Of course, if you have any questions, you're always welcome to email me, let me know. And next time we will probably talk about special relativity and things like that. But for now, I will see you next time.